Good morning, y'all. I hope that y'all had a wonderful day yesterday. All right, so yesterday in our 1 second timer lab, we started talking about something called simple harmonic motion. All right, you're going to see me abbreviate it a lot as just SHM. All right, so in our lab, we created something called a simple pendulum. And we started talking about how the motion, that back and forth motion of that simple pendulum, is a type of periodic motion. So any type of periodic motion is just a type of motion that repeats itself or repeats itself in a pattern. It can be predicted. So other examples of periodic motion are lunar phases. All right, so we know that the moon has the same lunar phases every 21 days. All right, the earth has day and a night every single day. All right, and that's because of the earth's rotation on its axis. All right, that rotation on its axis is a periodic motion. All right, whenever we have the same 4 seasons around the same time every single year, all right, that is due to the revolution of the earth around the sun. All right, that revolution is called or is a type of periodic motion. All right, so any type of periodic motion, again, is just any type of motion that follows a predictable pattern. All right, so whenever we talk about simple harmonic motion is a type of periodic motion. So not all periodic motion is simple harmonic motion, but all simple harmonic motion is periodic motion. All right, now the thing that makes simple harmonic motion different from other types of periodic motion is that just like whenever we looked at that simple pendulum yesterday in our lab, and like whenever we are going to look at a mass on a spring system, all right, these types of things are going to follow that pattern, all right, but they're going to do it around something called an equilibrium position. All right, you will also hear an equilibrium position called a resting position. All right, and that's going to be the position that these things are at if we just left them alone. All right, so if we were not swinging that pendulum back and forth, all right, if it was at rest, it would be straight down. All right, so this point right here is a simple pendulum's resting position. It's its equilibrium position. All right, so the periodic motion comes from it swinging back and forth around that equilibrium position. All right, so we're going to be looking at simple pendulums, which is what we see right here, but we're also going to be looking at a mass on a spring system, which is what we see right here. All right, so here we have a mass on a spring, and if we just left that mass and spring alone, we didn't touch it, this is where it would be. This is its equilibrium position. But as soon as we pull it back some distance, just like we pulled this back some distance, it's going to cause that mass and spring to go back and forth, back and forth, back and forth around that equilibrium position. And that is what makes it simple harmonic motion. All right, so right now, I'm going to be going over this in just a second, but right now I want you to just highlight this. All right, but what I really want you to see is that we compare a simple pendulum and a mass on a spring system. They act the same way. All right, so they Yeah, they act the same way. All right, so what we are looking at here with the simple pendulum is we have pulled it back to some distance. All right, that's going to be its maximum displacement. Well, whenever we let it go, it's going to fall down and it's going to go through its equilibrium position, and then it's going to go up, and then it's going to go back down through its equilibrium position, and then it's going to go up to its maximum displacement. All right, so what we are seeing here is one full cycle. All right, this is one full cycle of a pendulum. All right, so it goes forward and then comes back. All right, well, if we look at the mass on a spring system, that's right next to it. All right, we stretch it out some distance. That's going to be its maximum displacement. Well, whenever we let it go, it's going to go towards its equilibrium position and keep going. And then it's going to go back towards its equilibrium position and keep going. So what we are seeing here is yet another full cycle. So what I want you to look at here is how many times these things pass through their equilibrium position as they complete one cycle. And hopefully you are seeing that they go through that equilibrium position twice every time they complete a single cycle. All right, so we're going to focus first on just a simple pendulum, and this is where we're going to talk a lot about this. All right, but again, looking at comparing these, we can see that they act the same way. All right, so we saw this whenever we were talking about the conservation of energy. All right, so we talked about how at the very highest point, this point B, it's not moving, so all of the energy is its maximum potential energy, gravitational potential energy to be exact. All right, and then as it falls, it's going to speed up. And as it falls, that potential energy turns into kinetic energy. And then at the very bottom, it has nowhere else to fall. So all of that potential energy has turned into kinetic energy. Well, we know that kinetic energy is energy of motion. So that tells us that at this equilibrium position, it has its maximum velocity. So at its equilibrium position, it has its maximum velocity because that's where the kinetic energy is at its maximum. All right, but we know that it's going to keep going, and as it keeps going, that kinetic energy is going to turn into potential energy. All right, well, as it climbs, it's going to slow down. It's going to come to a stop, and then it's going to change direction and then speed up going down, and then it's going to slow down as it turns back into potential. It's going to stop, and then it's going to change direction and speed up as it goes down. All right, so what we are seeing here is this constant transformation from potential energy to kinetic energy, back to potential energy, back to kinetic energy, back to potential energy, so on and so forth. All right. But what we really need to look at is even though at its resting or equilibrium position where it has its maximum kinetic energy and it has its maximum velocity, on the edges, so these points are its maximum displacement. All right, this is where it is away from its equilibrium position the most. All right, so at its maximum displacement, you have the slowing down, coming to a stop, changing direction, speeding back up. So what you are seeing at these points are the points where it has its maximum acceleration. All right, so it has its maximum velocity at its equilibrium position, but it has its maximum amount of acceleration at its maximum displacement points. Okay. All right, so that's what we were comparing right up here. It's the same thing. All right, so its speed is at its maximum at that equilibrium position. Its speed is at its least at the maximum displacement. All right, and we see here that because its force is at its maximum displacement, so is the acceleration. All right, so we're looking at the same situation in both of these. All right, so still thinking about this simple pendulum. All right, we have something called a restoring force. All right, so this is the force that is trying to bring these things back to their equilibrium position. Well, with the pendulum, whenever we pull it up and let it go, gravity is the force that is trying to bring it back to its original position. So, or its equilibrium position, or its resting position, whatever you want to call it. All right, so gravity is the restoring force for our simple pendulums. So if you have more gravity somewhere, that's going to pull it down faster. If you have less gravity, it's going to pull it down a little bit slower because you are lessening that restoring force. All right, one other thing that I do want to make mention of, we saw this in our lab yesterday. All right, I did make mention whenever we were pulling our timers back, our pendulums back, I told you not to do it at a large angle. And that's because whenever you get over a certain angle, your paths are going to become very unstable. That's whenever they start going in all kinds of directions and you have this wonky path happening. All right, so simple harmonic motion happens with angles that are at 15 degrees or less. Now, yesterday in the lab, I told you to use an angle of 30 degrees. All right, and that's just because it's better for you to see. All right, it was just easier for you to see in our situation. But if you did it, it was still not that big of an angle. All right, so it's super important for us to remember that simple harmonic motion is only for small angles whenever we are talking about these simple pendulums. Now, one of the main things, this is one of the most important things in our notes today, is talking about the period of a simple pendulum. All right, so we kind of introduced this yesterday. A period is a measurement of time, hence the reason we use this capital T. All right, so it's the time that it takes to complete one cycle. And for a pendulum, that is it going forward and then coming back. All right, so it's the time that it takes to go forward and then come back. All right, so yesterday in our lab, what we were really looking at is what affected the period. All right, so in the first part, we saw that the length was definitely affecting the period. We saw the shorter the length, the faster it went. All right, so the shorter the length, the shorter the period. All right, and whenever we talk about gravity, all right, that as that restoring force, remember we just said if we have less gravity, that's going to be less of a pull down, so it's going to move slower. So we're going to have a larger period. It's going to take longer to complete that one cycle. All right, so if we are talking about the period of a pendulum, it only depends on two different things, and that's the length of the pendulum and the amount of gravity present. All right, and we can see that in this equation. All right, so we see that we have length and acceleration due to gravity. Those are the only two things that it depends on. The other thing that we were trying to figure out if it affected the period in our lab yesterday was mass. And hopefully, as you were doing the experiment, remember you kept the length the same, but we were adding more mass to it. And hopefully in your experiment, you saw that the mass did not affect the period at all. So your time should have been the same for your first mass as it did whenever you added all three masses together. All right, so your mass does not affect the period of a simple pendulum. All right, now as we're talking about pendulums, I want you to go look these up. These are some of the coolest things. I absolutely love them. They're everywhere. I mean, there are tons of them out there. There's something called Foucault pendulums. All right, so this scientist created this experiment. All right, this was one of the first experiments to give a simple, direct evidence to Earth's rotation. All right. And what's actually happening, you have this pendulum that's on a tension rod, so it's able to move freely, unlike a grandfather clock that has just one single path that it has to take. All right. So on this picture, you see that this one has a compass at the bottom of it. All right, others have like pits of sand. Those are my favorite. And as the day progresses, it's going to change direction. And so you would actually see the Earth rotating underneath this. It looks like the pendulum is changing its direction on the ones that show a compass, and the ones that have sand in them, the reason that they're my favorite is that they have different geometric patterns drawn in them as the day goes on. So it's actually the Earth revolving underneath the pendulum. So they are super cool. Like I said, you need to go look them up, see the different types. They're just a really cool experiment. All right, but now we're going to get into our examples. Enough with my nerdiness. All right, now we're going to get into our examples. All right, so for this first one, I want to know what is the period of a pendulum with a length of 2.4 meters on Earth. Now, the 2.4 meters is our length. That's really our only given, but I kind of specified on Earth because we know that the acceleration due to gravity on Earth is 9.81 meters per second squared. All right, so because we are solving for period, we do not have to rearrange this equation at all. Hallelujah. All right, so this is just a plug and chug equation. So we're just going to plug all of our numbers in. We have 2 pi times the square root of 2.4 over 9.81. Now, notice I did not put a negative right here. Now, we know G is acceleration due to gravity. We know that gravity is always pulling you down, so we do know that it's always going to be negative. However, we cannot put a negative under a radical. That'll give us an error in our calculator. It's an imaginary number. And we're solving for period, which is a unit of time. And time can never be negative anyway. So for this, we're just going to disregard, all right, that negative. So if we plug that into our calculator, depending on what you put in for pi, like I just put in 2 times 3.14 into my calculator. If you actually press in 2 times pi, you do have a pi button, it'll give us a few different answers. So for me, my answer was 3.08. I have a couple of people that got 3.10. I had a couple of people who got 3.11. All right, all of those are super close together. If we just got one single decimal for all of those would be 3.1 seconds. All right, so time period is a measurement of time, so it's always going to be in seconds. All right, so what this is telling us is that this particular pendulum with this particular length will complete one cycle every 3.1 seconds. All right, so this next example, you need to know the height of a tower, but darkness obscures the ceiling. You note that a pendulum extending from the ceiling almost touches the floor, and you calculate that it has a period of about 12 seconds. I want to know, how tall is the tower? All right, so we are given our period here of 12 seconds. We know that we are on Earth, so our acceleration due to gravity is 9.81 meters per second squared. We are actually trying to figure out the height of the tower by figuring out the length of the pendulum. All right, so we do have to rearrange this equation. All right, so we start off with our original equation. We're solving for length. All right, so the first thing that we're going to get rid of is that 2 pi. All right, well, technically that 2 pi is being multiplied. So we are going to divide both sides by 2 pi. That's going to get rid of that. So we have our period divided by 2 pi is equal to the square root of our length divided by gravitational acceleration. Now, a lot of people go ahead and try to multiply both sides by gravity, and we can't do that because both length and acceleration due to gravity are under that radical. So we have to get rid of it first. And to get rid of a square root, we do have to square both sides. All right, so that gets rid of that square root. I'm going to bring it up here. So we have our period divided by 2 pi. Now, let me make mention here, up here, it didn't matter because we were multiplying. But here, we have multiple things in the denominator. So we always have to remember that when we are putting this into our calculator, you have to include those parentheses around 2 pi. All right, we're going to square that whole piece. Now that equals length over acceleration due to gravity. And only now are we able to multiply both sides by acceleration due to gravity. So our length is equal to our period over 2 pi squared times acceleration due to gravity. So that's going to be 12 divided by 2 pi squared times 9.81. All right, we should get a length of the tower, of the length of the pendulum or height of the tower is 35.78 meters. All right, now this one is more conceptual. You saw this question or a question of this type on your lab yesterday. So say that you have a grandfather clock that is running on perfect time. It's keeping perfect time. All right, but then you take it to your summer house that is super high in the mountains, so high altitude, where we know we have a little bit less gravity. All right, so we want to know, is this grandfather clock going to run faster, slower, or is it still going to keep that same perfect time? All right, well, in answering this, we have to remember that gravity is our restoring force. So again, if we have less gravity, that is going to pull it down a little bit slower. All right, so it's going to run a little bit slower. Now, what that means as it runs slower, a lot of people get confused about this. Because it is moving slower, that means that the period is actually getting higher, right? We have a longer period. We're increasing the period because it is moving slower. All right, so hopefully you are doing okay with simple pendulums. Now we're going to move on to our next thing, which is the mass on a spring system. Okay, so that's what we saw right here. All right, so we have this mass on a spring system. We have its equilibrium position. We know that if we stretch it, we already said it's going to move back and forth, back and forth, back and forth around that equilibrium position. All right, so instead of gravity being the restoring force for this mass on a spring system like it was on the simple pendulum, we should note that the restoring force is coming from the spring. All right, you stretch the spring out, so it wants to get back to its equilibrium position. So it's going to pull that mass back and forth. So that restoring force for a mass on a spring system is not going to be gravity. It's going to be the spring force or that elastic force. And we've actually already talked about the spring force or that elastic force whenever we talked about Hooke's law. All right, so we know that Hooke's law, we saw this whenever we were talking about elastic potential energy and springs. All right, so that F stands for our elastic or spring force. Okay, and remember, we just said it's that spring force or elastic force that is our restoring force for a mass on a spring system. All right, so Hooke's law tells us that that elastic force is equal to negative kx. Negative kx. All right, so we should remember that K is our spring constant. All right, that's what tells us how strong, how stiff, or how flimsy our spring is. And then X is how far it has either been stretched or compressed. All right, so the big thing that we need to see right here is this negative. All right, that negative right there tells us that our elastic force is always going to go in the opposite direction as the motion of the spring. All right, so somebody said today, I asked, why is it always negative? The answer is restoring force. Somebody said, because K is negative. No, K can never be negative. And for CP purposes, our X is not going to be negative either. All right, so what we need to remember is that that force, that elastic force is always going to be negative because it is that restoring force. It's always going to be opposite the motion of the mass. All right, so because we're not dealing with gravity anymore, so we're dealing with a mass on a spring system, it no longer depends, the period of a mass on a spring system no longer depends on length and gravity. Okay, so it doesn't care about length and gravity. The only two things that it depends on is the mass that's attached to the spring. Excuse me. And the actual spring constant. So how stiff or how strong or how flimsy that spring is. And if you think about what's happening, it should make sense. So if I have the same mass attached to two different springs, all right, one has a higher spring constant, which means that it's stronger. One is attached to a flimsy spring that has a very low spring constant. We should imagine that the higher spring constant, the strong one, is going to pull that mass back faster. All right, so the higher the spring constant, the lower that period is going to be because it's going to be moving faster. However, if you have the same spring with two different masses, all right, the heavier mass is going to take a lot longer to pull back. So the heavier the mass, the larger the mass, the longer it's going to take, the larger the period is going to be, the higher the period is going to be. All right, so let's look at this. We have a 24-kilogram child who jumps on a trampoline that has a spring constant of 364 newtons per meter. We want to know what is the oscillation period. All right, so we're looking for the period. We know that the mass of the child is 24 kilograms, and we know that it has a spring constant of 364 newtons per meter. Well, because we are solving for period, we do not have to rearrange our equation. So it's just a plug and chug equation. So we can just plug in mass and spring constant. So we have 2 pi times the square root of 24 divided by 364. So we plug that in and we should get a period of 1.61 seconds. So that means that this has an oscillation period. It's going to complete one cycle every 1.61 seconds. All right, now this one, as Danny stands on a bathroom scale whose spring constant is 220 newtons per meter, the needle on that scale vibrates from side to side. All right, so we have it oscillating about an equilibrium position. So we see that simple harmonic motion. And if Danny has a mass of 180 kilograms, what is the period of the vibration of the needle? All right, so once again, we are looking for the period. All right, we have the spring constant of 220 newtons per meter, and Danny's mass is 180 kilograms. All right, so once again, because we are solving for period, we do not have to rearrange. However, you do need to know how to rearrange these. All right, so if you need help with that, you need to come see me. All right, but we are just going to plug in our numbers. So that's the square root of 180 divided by 220. Plug that into your calculator. You should get a period of 5.68 seconds. All right, so that means that this completes one cycle every 5.68 seconds. All right, so we are going to do more practice with this. We're going to expand upon this later on this week. All right, but as always, if you have any questions, you know where to find me.